I feel that we are on the verge of making a totally new theory of the gravitational force and of space-time. I think that things like inflation or even Big Bang is only approximation of what really happens. Just the idea that we can find the final laws, I think, is hubris. If you ask me where does the world come from, probably my answer would be quantum chaos. I feel there's some big thing to be done.
Renowned Professor Erik Verlinde, a legend in quantum gravity, thinks gravity is thermodynamic, specifically the thermodynamics of quantum information doing something, the way gas pressure is another way of saying molecules are doing something. Now, what that something is and how gravity could possibly look like this is the topic of today's podcast. And what's fascinating is that if you follow his results, you get two seemingly unrelated puzzles being solved, popping out automatically: the origin of dark energy and the origin of dark matter. No dark matter particles, no extra parameters.
I think that the particle dark matter community is not always playing this game honestly.
This is all because in 2010, a landmark paper by Verlinde derived the gravitational force from entropy and also derived inertia itself. That's Newton's F equals ma. To some, this transcends Ted Jacobson's celebrated 1995 result, which already assumed spacetime existed. I've spoken to Jacobson here, link in the description. But unlike Jacobson, Verlinde doesn't assume spacetime.
I think there's a next theory to be discovered.
I go into more detail on my Substack post here about both Ted Jacobson's theory and Verlinde's entropic gravity approach. Remember, to Einstein, gravity serves as a metonym for the curvature of spacetime. But today, the professor erases even that. Why? Because of entanglement.
I mean, space and time is something quite weird if you think about it.
The quantum information of spatial relations are correlated, and the magnitude of that correlation scales with the area of the surface between them. My name's Curt Jaimungal, and on this channel I interview researchers regarding their theories of reality with rigor and technical depth, primarily focusing on theoretical physics, but often also talking about philosophy and consciousness and free will. This channel is called Theories of Everything, but today we explore why there may be no final theory of physics. And Professor Verlinde means that literally.
I don't believe that we'll ever get to what would be the fundamental laws.
We also talk about why the cosmological constant problem may be a red herring, and why, when asked where the universe comes from, Verlinde's answer is one word: chaos. Professor, do you think we'll ever be able to write down the fundamental laws?
I mean, we being humans, I think we have some understanding of the universe and the laws of nature, and we'll always make progress. But I don't believe that we'll ever get to what would be the fundamental laws, because I think there's always more than that we can understand as humans. And also, I think the laws that we have been able to get are always, universal, but not always applicable. I mean, there's always exceptions to what we don't fully understand. And I think there's always, situations where our laws will break down. So I believe more that what we will discover are things that are eventually understood from, assuming that there's something more fundamental, more microscopic going on, and that the laws that we are discovering are kind of more emergent from that underlying more fundamental description. And maybe we don't really need to know what this fundamental description is. We can still apply general reasoning to find these emergent laws. I mean, this is something that we have been very successful at in the history of science. I mean, we have discovered the laws of thermodynamics before even knowing that there were molecules or atoms. But eventually we were able to derive them from the assumption that there are atoms and molecules. So sometimes a law that we find gives us also a view of what might be underneath it. And I think many of our laws, and actually all of our laws, are eventually of that kind, in the sense that I think we will find those emergent laws that come from something more fundamental underneath, where as humans we may be not able to really write down the equations that describe everything. I mean, so I'm not a believer of that there will be a final theory where we indeed, when we write it down, there's nothing more to be discovered. I think as humans, we'll always can continue and discover more, and there are always deeper questions that we have not been able to find. I mean, there's no final theory of nature.
But you do believe the final theory of nature exists? It just may be inaccessible to us as people?
I don't think that theory already is some assumption that we can sort of condense it into some finite set of equations. And I think our equations and everything that we have sort of developed as a language of describing nature is always a condensation of what is actually going on. I mean, I think the most well, maybe we should accept even the universe is so complicated that it's just the most efficient way of doing everything that's in there, and that there's nothing there that we can write down that will predict all of the things that happen in the universe. And so I think there's a limitation there. I think it's not like we can assume that we as humans will be able to write down such equations. And even the concept of equation is kind of something that we thought about as humans, but maybe the language in which we have to write down, or in which nature is sort of written down, is not something that is an equation, or it's something that we can, as humans, can ever even get to.
Now, are you thinking about it in terms of an effective field theory, that there are high energy degrees of freedom that are irrelevant to us at some scale? Or is what you're saying about that there's something that's going to be more fundamental, quote unquote, microscopically, and it's just emergent levels that we have access to? Is that transcending even effective field theory? It's something that's independent of it.
So effective field theory is one of those other examples. I already mentioned thermodynamics as a very important example, where we sort of assume that there's some molecules and atoms that do certain things, and then Boltzmann was able to derive the laws of thermodynamics. Another example, and that's the one you're mentioning, is by Ken Wilson. I mean, I think his point of view on nature is very important. I mean, he realized that what we now sometimes call our most fundamental theories are actually field theories that should be thought about as effective field theories, where there's always some more fundamental, sort of more microscopic, uh, description. But what Wilson assumed is that the more fundamental theory is always going to smaller scales. He always said the fundamental theory is more microscopic and more underlying it. And he was assuming something about what we call scales, in the sense you have the small scales and the heavy particles and things like this. And if you forget about them, you get this effective field theory that you talked about. So effective field theory is indeed a very important concept in nature. But one of the things that we learned is that when we start adding gravity, I mean, the gravitational force, it somehow doesn't really fit very nicely in this whole effective field theory approach. I mean, in the sense that we would like to quantize gravity in a way where we don't need to assume that there's some, well, what we call usually cutoff, in the sense that we say there are some degrees of freedom that we don't take into account. So I think what we have learned in string, I'm also studying string theory, which is kind of a approach to quantum gravity. And there you see that there are situations where this reasoning of Wilson actually breaks down. So I think that Wilson was on the right track, but that we need a more general idea of that kind that will connect, what we call the more fundamental description to what we actually see today. Because, I mean, our theories will always be, as I said, in the current language at least, something that approximates what was a more fundamental description.
I'm curious about this word microscopic. So, viewers who are listening or watching, they may have other views of what microscopic means. So, one may be that you view it through a microscope, another is that it's 10 to the minus 6 meters to 10 to the minus 9, somewhere between that range. But then another is just that you keep zooming in. And even this language that I'm saying, you keep zooming in to look closer and closer, implies that we're zooming in more spatially. Now, I've gone through your work extensively over the past few weeks and even months, and my understanding is that you've changed to even derive space itself from something else. So help me understand this word microscopic.
Well, microscopic means that it's also more fundamental, and there's some way in which we have to even change our language. I mean, space and time is something that we have introduced as a reference frame in which we formulate the laws of physics. But if you think about the changes that have taken place within physics, I mean, when Newton wrote down space and time, he thought it was something absolute. When Einstein was thinking about it, he realized, well, space and time can be relative, and what you call time may be not the time of another observer. So we started thinking about space and time already in a different way. So what we are learning now is that there's something that even space time should be made of. I mean, there's some way in which space and time can be constructed out of other underlying description. And so I think currently we are actually, even in my, I mean, I'm not the only one talking about this. I mean, in my field, we're really thinking about the microscopic description in a more abstract way where space and time are not even assumed right from the beginning. I mean, there are some ways in which, for instance, we have microscopic theories that are living, say, only very far away on some boundary of the space, and then somehow the space-time can be made to emerge from this more microscopic description. So what we call microscopic doesn't necessarily mean microscopic in our own space where we go smaller. It's more like it's a more fundamental description where the things that we write down really have a meaning in every scale, but also in the more, yeah, I mean, how to say it, underlying description. So mathematically, what it means, you write down first the equations that are for this microscopic theory, but I put it in quotation mark. It doesn't really mean that it's at
Right.
microscopic scales. But then you start deriving the properties that we see in our space and time from that, where space and time themselves are already not assumed from the beginning. So there's some way that space and time may emerge also from this microscopic language or description.
This entire line of thinking that there may not be fundamental laws that we have access to, in fact, even just saying fundamental laws itself is theory laden. Did that just start to occur to you later on in life? Because presumably, most people who enter physics, theoretical physics, do so because they heard about Einstein and they want to finish Einstein's dream of unification and finding the fundamental laws. So my question is about what motivated you to get into physics, and then how did your line of thinking as to what the fundamental laws are and our relationship to them and fundamentality and so forth change?
So I indeed started in physics, where the theory of everything, which is sort of what's even the name of your blog or your whole podcast.
Yeah.
I mean, it was kind of this fundamental idea, and it's true that Einstein is there on a pedestal, but Einstein is human. I mean, his theory is century old, and we have learned a lot more. And I have learned to be skeptical of other people's idea. I follow my own intuition. It's not like if someone tells me you should find the theory of everything, that the only thing I think about is that I should find the theory of everything. So I already started sort of, well, this is what's called intuition. I mean, you start feeling that cannot be the right answer. And that even has to do with sort of more of a philosophical idea. I mean, already you asked the question, can we ever find the final laws? I think as humans, we have limitations. So just the idea that we can find the final laws, I think, is hubris.
Interesting.
And if you really realize this is really a far-fetched idea that we as humans could ever be as clever to find the final theory, you start realizing it's the wrong track. It's the wrong question. But of course, you realize that Einstein and other very clever scientists, I mean, they found very fundamental equations that seem to apply almost everywhere. So how was this possible? And then you start realizing that as humans, we have been able to take what we observe and condense it in very small set of equations or experiences. That's what we do with our brain. We have so much information that gets in our brain that our brain is very good at condensing information and make it into very abstract notions. I usually use the example that if I draw this picture, people can recognize a house or something like that. Well, I've
Okay.
not drawn a house of that. I've just made some lines, and people can see. Well, that looks like maybe the lines are representing what a kid draws as a house, but it isn't a house. It's an abstract notion of what a house is. And so we do the same thing in physics. We take something that we have observed and we give it a name and we give it an equation, a symbol in some equality and so on. But I think eventually nature is much more complicated than what we have done. We have really condensed everything in a much smaller parts. And this is why I think eventually what we write down will never be the full truth, but always a condensation of what's really going on. Sort of an abstract. So I think that in this idea of emergence, which is a much more general idea, is that there's always something more fundamental. So one of the analogies that I sometimes use is that there's this story about, well, people wondering why the earth didn't fall.
Right.
You know this? Well, people had in some ancient religion then the idea that there is maybe some giant turtle that is keeping the earth from falling because it has it on its back. And then they were happy because the turtle was keeping the earth from falling. And then people said, well, what about this turtle? Why doesn't it fall? And then the answer is, it's turtles all the way down. And so I see every layer of the theory that we are making as one layer deeper, where we can make one step further, where there are some theoretical descriptions that we have found, like what we have now with the standard model and with general relativity is a beautiful description, but it's not complete. There must be a more fundamental one. But if you ask me, is that the final one? No, there will be another theory below that, another theory maybe below that. And so there's some way, I believe in this idea of what I call turtles all the way down, that we always will find the theories that are naturally emergent from the layer that's beneath it.
Okay, so there are a variety of questions I have. You said two interesting, more than two interesting, but two that stick out to me statements. So one was that you follow your nose. I want to know, were you always like that? Or did you have to train yourself to be like that? Okay, so let's bracket that because we can get back to that, but just a moment. And then number two, you said finding the fundamental laws may not be the right question, which then raises the question of what is the right question.
Now, that's a very good one. I mean, and I have to say that of course, when you enter physics, you have an ambition. You want to find new things that other people have not understood. That's one thing. One thing I have to tell you also, I mean, maybe you know this. I mean, I have a twin brother. You know, I have a twin brother who is also interested in theoretical physics. So this is certainly someone that influenced me a lot in my life, because even in high school we were already talking about what we were reading and what we were watching on television about. Well, we saw Stephen Hawking and also in the documentary about indeed particle physics, and the person that later became our advisor, that was Gerard het Hoofd, was also featuring there. So we were discussing about particles, about gravity, black holes, and Herman and I. So Herman is my twin brother. We already were discussing a lot during high school and during our studies. We even had some other fellow students. So we certainly had already done a lot in thinking about physics and these equations. And there's some way that even sort of the mathematical language that we also learned, I mean, everything that you sort of learn in university and also in high school is about also this abstract thinking. And there's some intuition that you get eventually about what you feel is the right direction. And I think that as a physicist, as a theoretical physicist, you should have this feeling about what is the right direction to go into. Well, I mean, I think every great physicist had this. I mean, if you read quotes by Einstein I mean, he basically says it's not knowledge or even understanding is all imagination. That's the more important thing. That you have to be able to imagine things that other people have not been able to imagine. You have to go beyond the normal language that we use in every day. Because certainly when I write my equations, I have some image of what I'm writing down, but it's not always translatable to ordinary language. I mean, there's some way that we think in different terms than what we use in everyday life.
I remember the doubt before launching this podcast. What if no one listens? What if I'm wasting my time? If you've ever felt that way about starting a business, Shopify is the partner that turns uncertainty into momentum. They power millions of businesses and 10% of all US e-commerce, from Allbirds to Gymsharks to brands just getting started. No straggler left behind. Shopify's AI tool writes your product descriptions for you. It enhances your photography. It builds you a stunning store from hundreds of templates. Forget about the normative haze of bouncing between separate platforms. Shopify puts inventory payments and analytics under one roof with the propriety of a true commerce expert. Their award-winning 24/7 support means you're never alone. And that iconic purple Shop Pay button, it's the backbone of their checkout, the best converting on the planet, turning abandoned carts into actual sales. It's time to turn those what-ifs into with Shopify today. Sign up for your $1 per month trial at shopify.com/toe. That's shopify.com/TOE. Is the image that you have in your mind usually or always a visual one?
That's also a good one. I mean, I think it's close to visual, but not exactly, because there's also, I mean, as you know, I mean, one of the weirdest theories that we have discovered in the previous century was quantum mechanics. It's really where you have to rethink the logic of what we call our classical worlds. And I remember learning about it and being also initially totally confused. But at some moment, you start accepting that the world is quantum mechanical. And so there's then at that moment already a loss of the sort of usual visual things that we have in our brain, because I mean, it's not like I can compare it to any classical thing that I see around me, but you have some visual image. There's some, but to be honest, I mean, in your brain you can imagine things that are not even drawable. I mean, I find it sometimes even easier to not have a piece of paper and write things down, because then they're too visual. When I turn off the light and I have it just empty in my brain and I don't see anything, my brain can imagine more things than I can even draw on a paper. I mean, in the sense that there's more space there and more language there that I can use, that I can access, that is not expressible in terms of words, equations, or drawings.
Yes. Now, for me, it's conceptual. So it's a combination of visual, algebraic, but also conceptual. And I don't know how to express conceptual thoughts. I mean, to convey what I mean by when I think conceptually. Because when I think visually, that's easy. You can show that on a screen, video, and
now,
algebra.
Conceptually, I think is also indeed a very important point you're making, because in deriving, I mean, or developing physics, eventually you get new concepts. We already talked about emergence, which is a very difficult concept already to explain what it really is. It's really where you say that there's something fundamental, but that the equations that you write down or the description you write down at some higher level or whatever, I mean, the next level is sort of derived from that. But it's even more subtle. And so I also think that when we are physicists, we also have to work from a certain what's called a paradigm. There's some set of basic rules that you accept. I mean, if you say, well, the world is made of space, time, particles, and so on, we have a certain language that we are already assuming before we even start. And I think that's the language that people used in the 20th century. I mean, people said there's space, time, we have particles, we have forces, and then we have something that builds our universe. But I think the current language is very different. And so there's some jumps that you have to make when you start changing or introducing new concepts even also. And certainly, you're right. I mean, being a theoretical physicist also means that you're not just working with new equations or new, language. It's really new concepts also. Yeah, that's right.
I'd like to get back to something you said earlier about the house that you draw, and it's a stick figure, yet it's recognizable as a house. It represents the house, it's abstract, but it's not the house. Okay, so were you thinking that physics, as we know it, is the compressible part of nature, the part that we can take down and write simply, but that there are uncompressible parts? Is that what you were saying?
That's exactly what I'm saying. That indeed that the physics is the part that we can condense in very small, abstract part, as if it is a stick figure. And so this is what we can fit in our brain. But it is an approximation of the actual thing that's there. But it's a very good approximation.
Now, the second part to that is that these uncompressible parts, do you imagine that they are also all physical still? So I'm sure you've heard of physicalism, that all there exists is just physics, or what's described by physics. And then there are other ontologies like, oh, where does consciousness come into play? Maybe everything is consciousness. Maybe there's two aspects of the world, a physical and a mental. Maybe there's more.
I'm not entering that. I mean, in a certain way, I think it's physical in the sense, but I do think that one of the things that we have assumed, indeed, in I think the previous century, which is kind of what I call reductionism, is that everything is being reduced to smaller and smaller parts, and that we can sort of build everything up from the microscopic. That's sort of going back to this earlier comment of what is microscopic. There are certainly things that are there in nature that have nothing to do with being built up from the microscopic. There's something there that might be even macroscopic and at larger scales. And one of the things we are learning is that if we really want to understand the very large scales, we have to go back to what is also maybe the small scales or the other way around. I mean, there's some way that the large scale and the small scale are connected. But I agree that what we have probably described in our laws of nature is a condensation where we have forgotten many things about the universe or the microscopic or the full fundamental description that we have not really captured in those equations. And maybe that's also getting me to the insight I had about the origin of the gravitational force, because there's something that is kind of something that I learned from my brother Herman, actually. I wrote this idea about entropic gravity, which is sort of where I want to get to maybe next, is that there is a notion of, actually, it's called, actually, after sentences that Donald Rumsfeld used in a very different context. He had it over about known knowns,
the
right, things you know. There are also unknown unknowns, things you don't know that you don't know. But there's also something that is called known unknowns, things that you know that you don't know. And I think there's some truth to that, in the sense that there's something in our description of nature, that there are some things that we know that we don't know. And we can count, namely, how much we don't know. And this is what's called entropy. So I'll give you an example. There's something about, here at my room, you have a room there, and it's filled with air, and there's lots of molecules, and all those molecules are moving in all kinds of directions. They're all kinds of positions. And, we don't really know where they are, but we have a way of counting it. What's the amount of information that I need to put in whatever these equations to really describe what these molecules are doing? So then I have to write down all the positions, all the velocities of every particle, and so on. And you can count this. And this is called the entropy. So if I think about all the possible ways that molecules can distribute themselves around the room, that has a number associated. It is called the entropy, namely, and that is something that we know that will increase. It also is sort of a measure of I would say, almost the chaotic behavior of all these molecules, in the sense that they can do in all kinds of different ways. So we have some knowledge about what we don't know. We can count it. So in the amount of information that we do know, we have some knowledge, but we can also say, well, this is what I don't know. And that is quantifiable. But the insight that I got is that that amount of information that we don't know can actually influence things that we do know. I mean, there's some way in that forces maybe originating from this entropy. So if I take all of these molecules in this room and I put them in a small corner, clearly they have less entropy because, well, I need much less information to describe them because the amount of velocities and the number of positions is much smaller. But I also know that eventually they will fill up the room again because they start moving in all directions and they get much more space and much more velocities. And this is sort of a way that entropy can give rise to forces in the sense that if the entropy wants to increase, we know that we get things like pressure and so on. So one of the ways I think about the laws of physics is that we have not taken into account all those positions and velocities of the molecules. We've described it in terms of the temperature and the pressure, and that's usually enough to know what is going on, and it works very well. But that's a condensation of all that information that's there. We have forgotten a lot of information by just talking about temperature and pressure. And this is what we also do in our current law of physics, is that we forgotten about a lot of information that's contained in the space-time and so on, but we simply describe it, say, as some geometry of space-time or something like that. I mean, anyway, so all the equations that we normally write down in our laws of physics are just approximations where we ignored a lot of microscopic information.
So known unknowns just means that you can assign a probability distribution to it.
Well, a probability, but also really count how much it is not known, because we've come now to the language of information, and maybe I want to sort of make that point is that I think the language that we start currently developing in writing the more fundamental laws is that we don't think about space, time, or particles as being the most basic language. We start talking about more information. I mean, there's some new language that we are developing. I think every century that we have been doing physics had a different language. If you think about it, that, as I said, the 20th century was about particles, forces, space, time, and so on. Our current century is about information. If you think about how we even, well, design our world around us, we have no longer only whatever a television where there's some particles being accelerated. We have things that are, well, operating on data and qubits and bits and so on. And so there's a lot of different technology being developed that uses a very different language than the language that we have used in the previous century. I mean, we live now in an information age, and that also means somehow that the language in which we are writing the laws and even formulating the laws has also changed into, well, a different idea, namely that molecules or atoms are no longer the fundamental building blocks. It's bits of information that are we have to sort of use as our most fundamental language.
Usually information is about something. So information about a kettle in front of you or a cup, or information about a book, or information about words and so forth. So the information that you're saying underlies atoms is information about what?
So this is where I think information maybe is a word that we usually associate to something that we can know or something like that. But what I meant to say here is more like when the way we store data maybe on our computer. There are things that if you think in more microscopically what's going on in the computer, it's zeros and ones. Everything is being written in some code where there are zeros and ones, which are kind of telling me, well, one if it's true, zero if it's wrong, or something like that. But it doesn't mean that it has to be about something. Information can be really very abstract. As well, when you look in your computer, you can ask how much data is stored there. I mean, you can say it's so many terabytes. you don't need to know what it is, because there can be a lot of junk on your computer, but on the computer it just looks like zeros and ones, and every possibility of a 0 and a 1 is an amount of information. And so we can count information basically in terms of the number of bits or the number of bytes. And so for me, information is something that I think is, or maybe you should so call it data, is something that can be defined abstractly, independent of what it's about. It just means there's something more microscopic being stored there that is keeping track of something, but what that something is not important for us. It's really the amount of information that's more important than what it's actually about.
Does it ultimately have to cash out in aboutness?
No, this is exactly going back to the question whether we will ever know the fundamental laws. I think there's really a lot of unknown there, and therefore we should just be happy that we know how much is unknown. No, I think that well, how should I say this? I mean, space and time is something quite weird if you think about it. One of the things I always feel that it may be underappreciated is that why does the right-hand side of this room know that it's connected to the left-hand side? I mean, if I cut it in the middle, somehow, why doesn't it fall apart? And I think it's comparable to why I have a certain object, like, say, a glass, which has the same property, that it's connected. I mean, the right side knows it's connected to the left side. But that in the glass, we know why that's true, because there's molecules that are being bound together. So for space-time, we have to sort of go to a very similar language, that we have to eventually understand what it's made of and why its connectivity, how it can be explained. And this is where this more microscopic information comes in. And maybe I have to get indeed to the language that we are currently developing, because all of what I've been talking about now is actually being studied by not just myself, but by many colleagues in my field, is a more fundamental description of what space-time is, and where we indeed are thinking about why space-time is connected. And then we have to go to the idea of quantum mechanics, and also about these information bits, because in quantum mechanics, a bit is no longer a 0 or a 1, but it can be some superposition of it. And then the other weird thing that can happen in quantum mechanics, I mean, if a bit is in a superposition of a 0 and a 1, it means that there's a certain probability, if you start looking at it, that you get a 1 or you get a 0, and that probability, well, may be determined indeed by some microscopic description, some more fundamental description that we call the wave function. But in quantum mechanics, it's possible that some bit here, whether it's a 0 and a 1, is connected to what's happening to some other bit very far away, where if I measure a 1 here, I will also sure that it's going to be a 1 over there. And that might be a bit somewhere very far, or a qubit very far, say on Mars, or maybe in Andromeda, or even further out. But the outcome of the measurement here, which is, well, a probability of having either a 0 or a 1, determines what's going on the other side. This is something that Einstein already talked about with two colleagues called Podolsky and Rosen. And they thought it was very weird that quantum mechanics could do this. And they call this sort of a spooky action at a distance. Nowadays, we call this entanglement. It really means that there's some way that quantum mechanics, that it tells us that there's some connection between an object here and an object very far away. And so now the insight that we have recently been obtained in our field, like, well, recently means like whatever, 10 or 15 years ago, is that space-time is sort of understood from, well, by studying this amount of entanglement. So there's some way, this question about why does the right-hand side of this room know that it's connected to the left part, is precisely because it's entangled. There's some way that the things that are happening there are being entangled with the left. So quantum mechanics comes in, and we can even count how much entanglement there is. I mean, how many of those qubits are being entangled when I sort of separate the room into two parts. I can actually count how many qubits I kind of have been entangled in that way. Namely, the way this happens is that we have actually a relationship between the number of entangled qubits and the area of the space that I'm cutting. So if I'm cutting the space into two parts, I'm separating the room into two parts. So I have some surface here that has a certain area. It turns out that the magnitude of that area, the size of the area I'm cutting, is actually telling me how much entanglement I'm sort of breaking between the left and the right. So there's some way that when I cut the space, I really break the entanglement. Just like when I cut a glass, I'm breaking the connection between the molecules on the left and the right. And so this picture of a more fundamental description of space-time in terms of entanglement is really what's driving now our current understanding of what gravity is, and even what, well, this more fundamental language about what time and space are is about. It really starts with quantum mechanics, entanglement, and maybe other notions that kind of are not connected to particles or forces. I mean, the particles and forces are eventually derived from these ideas.
When I'm wrestling with a guest's argument about, say, the hard problem of consciousness or quantum foundations, I refuse to let even a scintilla of confusion remain unexamined. Claude is my thinking partner here. Actually, they just released something major, which is Claude Opus 4.6, a state-of-the-art model. Claude is the AI for minds that don't stop at good enough. It's the collaborator that actually understands your entire workflow, thinks with you, not for you. Whether you're debugging code at midnight or strategizing your next business move, Claude extends your thinking to tackle problems that matter to you. I use Claude actually live right here during this interview with Eva Miranda. That's actually a feature called Artifacts, and none of the other LLM providers have something that even comes close to rivaling it. Claude handles, inter alia, technical philosophy, mathematical rigor, and deep research synthesis, all without producing slovenly reasoning. The responses are decorous, precise, well-structured, never sycophantic, unlike some other models, and it doesn't just hand me the answers. The way that I've prompted it is that it helps me think through problems. Ready to tackle larger problems? Sign up for Claude today and get 50% off Claude Pro when you use my link claude.ai/theories of everything, all one word. To the viewer or listener who's wondering, well, what did you mean precisely when you said that the room knows about the left and the right, and that if you were to cut it in half, that it doesn't fall apart? What would it look like if the rooms fell apart? Like, what do you mean that the left and the right know each other in a room?
Well, we can move through space. I mean, there's some way that we can go from right to left and we can go back. There's some way that our space is something that we kind of fill up in the way that we think, well, I can go there, I can go there. So we can also describe it into something we call coordinates. I mean, if I have some distance in this right direction, I can measure the distance in terms of centimeters or inches or whatever. And there's some way that I can continue. So there's some way that space forms a continuous line in this direction and another direction. And this is sort of how we think about space. This actually goes back to Cartesius, where he really thought about these coordinates x, y, and z, and we can sort of make this all connected. But if I have a space that's disconnected, this kind of actually happens also, I have to say, in near black holes. I mean, there's some way that if we are thinking about, I mean, for me, actually, this is a very important part of our understanding of what gravitational force is about thinking about extreme cases where our gravitational force becomes very strong, for instance. And also for space-time, that's kind of a very important example. When space gets curved, and especially near black holes, what happens is that matter gets compressed so dense that it gets below a certain distance that light can no longer escape. And so near black holes, we have a situation that matter is so condensed that there's this sort of imaginary sphere around it that when you are behind this surface, you can no longer escape. I mean, this is what we call the horizon. So when we are on the outside, there's some, well, we cannot even look inside of a black hole because nothing can escape it. So we are basically disconnected from it. So there's some way that the horizon forms the boundary of our space. So I think about this also as basically cutting the space into two parts, where we say there's the outside and the inside, where the outside and the inside in a certain way don't talk to each other anymore. And it's precisely by studying this horizon that we are learning these facts about, that there's this amount of information that we should associate to the inside compared to the outside. So there's maybe here I have to indeed tell you about the other physicists that have been thinking about these ideas and sort of whose ideas have been influencing this. I mean, when I mentioned what I looked at with my brother in high school, one of the people that we watched was Hawking, who was famous already in the 70s for discovering very fundamental laws about black holes, where he discovered that black holes, when you include quantum mechanics, they emit radiation. But he also discovered, and it was together with Bekenstein, that there's a certain entropy, a certain amount of information that you can associate to black holes that goes exactly like the area of this horizon. And this is kind of a fundamental insight that actually makes clear that indeed the gravitational force is about information or about these properties like entanglement. So his insights play a crucial role in our current understanding of how to think about space-time and also about the more microscopic picture of space-time.
I want to get to entropic gravity. So, entropic gravity is a large umbrella, and sometimes it refers to Ted Jacobson's results, which we're not referring to here. And I would like to know the relationship between yours and Ted Jacobson. So, my understanding is Ted Jacobson used Clausius's entropy along with Rindler horizons to get Einstein's equations, whereas you are using it to get Newton's equations. Does yours derive Ted Jacobson's? Does Ted Jacobson's derive yours? Is there not an intersection between them? How do you view those two different approaches?
Well, Ted Jacobson certainly was the first to realize that this idea of we're skipping a step here, but this idea that there's some relationship between the horizon and entropy, this areas and entropy, can be used to derive the equations, the Einstein equations. Actually, it does go back to Hawking and Bekenstein. They wrote down laws that look like the laws of thermodynamics that apply to black holes. And so what Jacobson showed is that if you assume that the entanglement entropy, this kind of this quantity that we've been talking about, is equal to the area of some horizon surface, then you can derive the Einstein equations. Now, one of the things that I added to his theory, because certainly in my equations, I also like to talk about deriving the Einstein's equation, which is very important. But there's a much more fundamental step, because one of the things that I put in is that I said that Jacobson basically already assumed space-time. He assumed that there is an area. He said there is a entanglement entropy that goes like the area. Let's write down the first law, and then it becomes Einstein's equations. But I think there's something circular about the reasoning, because assuming space-time also is assuming its geometry. You cannot derive its geometry from something there. So what I realize is that, and this is sort of what I emphasized in my paper, is that the first thing that you have to get to is understanding space-time. And there's something more fundamental than just the gravitational laws. The gravitational laws are about forces that are changing just already Newton's first law. So Newton wrote down 3 laws, the first law being about inertia, the second law about the reaction is minus reaction, and the third law being the gravitational force. in a certain way, what Jacobson does, he derived the third law. Because if you derive Einstein's equations, you also derive Newton's third law, but you don't tell me how inertia arises. Inertia is a much more fundamental concept that basically tells you what mass means. How, when we move something, why do we apply a force? Need to apply a force to accelerate it. So F equals ma. That's the law that I derived, and I think that's also still a very important thing. Is that in the progress that we are making now, we're eventually not deriving only Einstein's equations. We need to derive first what space and time are. And so the fact that space and time are emergent is something that I emphasized in my paper and that he didn't see. So there's some way that my paper transcends his equations, his results. And I think it also contains it in some form. So I think the approach is different, but I think the emphasis that I made was much more on the emergence of space and time itself, and also on the fundamental laws that first need to be derived, namely the first law of Newton, the law of inertia.
Okay, so gravity emerges from thermodynamics. To me, that implies some equilibrium. But at the same time, we need gravity to drive structure formation. And that seems to me to be non-equilibrium, like manifestly so. So how do those two cohere?
Equilibrium means something in terms of the equilibrium in the particles and in everything that's filling the universe or something like that. It's kind of what we had. But if you ask what is driving the laws of gravity, it's not the particles that are doing this. It's really this microscopic building blocks of the space-time itself. And they are in equilibrium at horizons of black holes. They are at the equilibrium of the horizon of a cosmological horizon. They're not in equilibrium in some arbitrary point of space-time. And so there's some way that equilibrium can be distorted there. That's one thing. But the other thing is that the expansion of the universe and all the things that we use in our current formulation of the cosmology and structure formation are derived from Einstein's equations. So if you first want to derive Einstein's equations, then these other equations follow. But I think the more microscopic description might be quite different from what Einstein's equation already is telling us. So the assumption of equilibrium, I think, certainly goes into the laws of thermodynamics, but that only needs to apply sort of very locally in some very small neighborhood. And this is sort of also what Jacobson's argument was about. So that it's not like there's an overall equilibrium. So in a certain way, I should say the assumption of equilibrium is not what is necessary for deriving the Einstein equations or something like that. It's only anyway, I don't think there's a contradiction between those two ways of looking at it. So structure formation, I think, is something that eventually going to follow at a much later level in deriving those equations. So they're not connected to the equilibrium laws that we apply for gravitational equations.
Is entanglement entropy well defined in collapsing or non-equilibrium configurations?
Also a good question. People have so so we have a description of entanglement entropy in quite precise one actually in theories that have been studied for now more than 25 years. Actually, it goes back to the ideas of Maldacena, which was building on ideas of Bekenstein and Hawking, Susskind, 't Hooft. But anyway, there we calculated entanglement entropy in a very precise way. This work has been extended, where we also have dynamical situations where we can define entanglement entropy. I mean, there's names associated to that. Hubany, Rangamani, Hamilton. I mean, there's some people that have defined entanglement entropy also in dynamical situations. So there's no problem there. One of the insights we are having now actually is one of the big discussions going on is that there's more than just entanglement that's going to be important in this microscopic description. So entanglement entropy can be defined in those situations, but we have other things to worry about. I mean things like computational complexity. I mean, I'm just dropping a word here, but there are many more concepts. I mean, we're going back to that word that are playing a role in this microscopic theory. I mean, it's clearly going way beyond what we can discuss in this podcast, but we are really making progress in this defining all these um, physical concepts in situations that are closer and closer to what we really need to describe the real world. We're not there yet. I mean, it's clear that this theory needs further development, and I think we're making lots of progress, but we're still, well, years and maybe even decades away from having this better understanding and having what I would call sort of the next theory, where we indeed have found a more fundamental description of what we call nature, but maybe not the most fundamental. So I don't think that we will get to this most fundamental description, but we'll make progress towards a more fundamental description.
So when speaking about deriving space, in the Ryutaka Yanagi, if I'm pronouncing that correctly, the formula, it relies on a spatial region A. So does that not already encode locality, like a boundary geometry to derive the bulk geometry? So space doesn't emerge from entanglement per se, it's just the bulk emerges from boundaries plus entanglement.
You're right. We have some understanding of a microscopic descriptions in space-time where we have a boundary, which is called anti-de Sitter space. It doesn't look at all like the universe that we live in. And they have, I mean, the Ryu and Takanyagi, which is kind of indeed the people that have done this initial work, they studied entanglement entropy in this microscopic description. And this microscopic theory can be thought about as living on a boundary where already is some space associated with it. And it's true that it's very useful to have already some geometry there, but the emergent geometry is the one that we have sort of in the space, which we call the bulk. It's some additional direction that we have to add. You're right that the area that we define there is not totally emergent in the sense that already has some definition on the boundary. This is one of the reasons why I think ADS CFT is not the final story of how we're going to understand space-time, because we indeed have to get rid of this idea that there is a boundary, because our universe doesn't have a boundary of that sort. But it still means that we can make progress towards it. And I think what happened in the last decade maybe is using this Ryutaka idea and see how we can formulate it in ways where we can maybe get rid of this boundary. And so there's this dependence on the choice of this area that you're talking about. And this is where I think we need new concepts, not just maybe entanglement entropy, but also maybe this idea of complexity. But this is also where I think we are having trouble following the ideas, for instance, of Jacobson. Jacobson did assume that we can define entanglement entropy, did assume that we can identify it with the area, which is kind of what we and Takanyagi have done as well. And there are other people like, in particular, Van Ramstonk, I should mention his name, because this idea that space and time are connected because of entanglement is kind of due to Van Ramstonk. Also, Maldacena and Susskind have sort of advocated this, and they have this slogan which they call EPR is ER, which maybe you have heard about.
Yes, which I think you actually thought of a few months before. Wasn't there some email exchange in 2012 between you and Herman where you presaged this idea, but you didn't publish it? ER equals EPR.
That's correct. That is correct. We already had this idea, but I think at that time we already realized that the first idea really was due to von Armstrong. I think in that sense, the credit should be going fully to him. Although the slogan was, of course, invented by Susskind and Maldacena. But of course, I mean, there was earlier work by Maldacena where he also realized that when you entangle two conformal field theories, called that you get some connectivity and so on. So there's way that Maldacena certainly and Susskind also deserve it. But we had indeed this idea already. But that was in the context of black holes. And I think what we are learning nowadays is that we are maybe have to extend this idea of only using entanglement. So Susskind is also known for this slogan, other slogan where he says entanglement is not enough. And what he tried to add in that description is what's called computational complexity. And I do think that that notion is also important. So there are many steps that we still need to go through. But maybe what I wanted to say is that Jacobson derived the laws of Einstein, I mean the general relativity, from assuming that the entanglement entropy goes like the area. I mean, we can derive it using sort of these ideas that when we use Einstein's equations, we can derive it kind of, but we have then sort of worked the other way. So there's some way that the logic changes. So if we assume that entanglement goes like the area, we can derive the Einstein equations. But this is an assumption, and you may wonder whether that assumption is always true. And I think that there are situations where that might not be true. And this is where I was already saying that our universe is different from the one that we have been studying all the time, namely this anti-de Sitter space. And maybe things work differently there. And I think I'm actually convinced that when we start redoing our analysis of how to derive Einstein's equations, that in a universe where there is dark energy, which is more like our own universe, that there can be deviations from it. And so I hope that our quest in understanding where the gravitational laws come from will help us understand what is dark energy and even what is dark matter. So there's a lot of things, I think, to be discovered there.
The Economist covers math, physics, philosophy, and AI in a manner that shows how different countries perceive developments and how they impact markets. They recently published a piece on China's new neutrino detector. They cover extending life via mitochondrial transplants, creating an entirely new field of medicine. But it's also not just science. They analyze culture, they analyze finance, economics, business, international affairs across every region. I'm particularly liking their new Insider feature. It was just launched this month. It gives me, a front row access to The Economist's internal editorial debates, where senior editors argue through the news with world leaders and policymakers in twice weekly long format shows. Basically, an extremely high-quality podcast. Something else you should know about is that if you go to their app, they not only have daily articles, but they also have long-form podcasts with their editors and writers. This is also available online. Whether it's scientific innovation or shifting global politics, The Economist provides comprehensive coverage beyond headlines. As a TOE listener, you get a special discount. Head over to economist.com/TOE to subscribe. That's economist.com/TOE for your discount. Yes, you've connected dark matter and dark energy, and I'd like to know more about that. Kuhmann-Waffa has also connected dark matter and dark energy, but it's a different idea. It's dark dimensions, it's Kaluza-Klein gravitons, and so yours isn't that.
That's correct. No, it's connected to the idea that the world, the universe we live in, is, as I said, a very different one than the one that we've been studying so far, which is called anti-de Sitter space. Anti-de Sitter space you think about as a universe without dark energy. So the space that we have has dark energy in it, and it creates a very different space-time where there's a horizon, very much like the horizon of a black hole. There's also entropy associated to that. And many of the ideas, especially this Ryuta-Geniagi idea, or some generalizations of that have been recently studied, what's called quantum extremal surfaces and so on, they don't apply to this kind of universe. And you see that there's different microscopic descriptions required to understand how this positively curved, the space that space-time that we have now with dark energy, how that is going to be described. I already mentioned this word computational complexity, which I think is going to be crucial in understanding this. But what we have to do is to go back to this derivation, basically the derivation of Jacobson of the Einstein equation. So how do we derive it? If we don't have these assumptions that the entanglement goes like the area, if there's some other form of entropy that's in that universe, then you will find other equations. And I have found actually, it's going back actually to discoveries by Milgram about ways in which galaxies and their rotation curves behave. He found a connection between where the rotation curves of galaxies start deviating from what is described by Newton's and Einstein's equations, and the cosmological expansion. Some way in which our cosmos is behaving. And that discovery and that connection, I think, is quite an important one, because it actually tells us indeed that the expansion of the universe, the way that we are viewing the stars moving away from us using this Hubble constant, that's also telling us where this horizon is sitting, because if things are moving away from us at a speed that increases with the distance, there will be some distance in which it's moving away with the speed of light that we call the horizon. That actually also tells us how much entropy is there in the universe. So what I discovered is that by thinking about this entropy, you can actually explain the observation that Milgram made, namely that there is this deviation from the gravitational laws exactly where we are observing it in these galaxies. Yeah, so anyway, I think that is something that needs further development, and certainly theoretically we have to understand it much better. But it's certainly the area in physics where we're gonna make a connection with observation, because I think our theoretical explorations of what quantum gravity is so far have been very far from any observations. But I do think that these cosmological observations about dark matter and so on are actually due to effects in quantum gravity. And therefore, that's our hope to finally make a prediction or have some observation of something that where we can test our theories.
Yes, you derive Milgram's acceleration as equaling a sixth of the Hubble constant. So, as far as I know, you're the only person who's done that from first principles. I could be incorrect. Are you aware of any other approaches that get that same result?
No, but I have to say that of course I was aware of the work by Milgram. I have this idea of how to connect it to the ideas of emergent gravity, and I wanted to see if that could work in also explaining the actual phenomena that we are observing. And I wrote down what I would call also an effective description. As I already mentioned, I think our theoretical understanding has to be improved. And I like to eventually motivate my colleagues also who are thinking about gravity and the way it's emerging from a more microscopic quantum description in terms of, well, entanglement or complexity and so on, to even think about those questions, because I think we have really a chance to verify our ideas in observational facts. And if that happens, of course, that would be spectacular. But I'm quite convinced, actually, at this moment, that this is going to be happening, and I hope it's going to be even generally kind of accepted in the next 10 or 15 years, because I do think that our program of understanding gravity more fundamentally from quantum principles and quantum information is going to lead to these modified equations for the gravitational force. And anyway, we need to make a lot of progress in our theory to see how we can make that more precise. But certainly nowadays, I think actually currently we are even discussing many problems about this kind. I mean, there's one of the conferences I went to last month in December actually. It was about precisely how we can think about the gravitational force or even the emergence of what are called closed universes. So where we have universes without boundary, not like anti-de Sitter space. So that is actually a very exciting development. And I think that it's going to go in the direction that I was already envisaging. I mean, there are some ways in which many of the assumptions that I made, or how should I say, the intuitive steps that I made in my description are being verified in that context.
What would a boundary bulk duality look like in the case of a closed universe?
There's no boundary, of course. So I think the idea that the microscopic theory lives on the boundary, I always think that was was not a relevant thing, in the sense that I think people confuse themselves in the sense that there's a microscopic theory, it lives on some space, and there's the bulk theory, it lives on some other space. The fact that the space on which the microscopic theory lives happens to look like the boundary is not the same as saying that it lives on the boundary. I think people have I think that's really a oversimplification of what's going on. And so what I think is true even in closed universes is that there is a microscopic theory. But you're going to ask me, what space does it live on? I don't care about what space it lives on. It should be a microscopic theory. It doesn't really matter. It doesn't need a space. The space is emergent. It's not like, and that's actually going back to your question, that in re-heterogeneity, space doesn't entirely emerge because we already assumed that the microscopic theory was living on some space. I think it's much nicer if you don't assume anything about the microscopic theory. It doesn't need to live on some space.
Now, we've spoken so much about space and not much about time.
I like that. Go ahead.
Are observers necessary for time?
I don't think they are necessary, but they're very useful in the sense that they experience time, and they also tell us which part of space we have to consider. So if you are living somewhere, you can only observe a certain part of space, and there's a certain part that you cannot see. And it's certainly true that in the microscopic description or the fundamental description, there are parts that we observe and there are things that we cannot observe. Now, one of the nice things that I have been, studying myself a lot recently, but also that many other people have been looking at, is that you don't need time to even have time emerge. So we can have space emerge, but there's also time can also be emergent. It also emerges from entanglement in a very nice way. And this has to do with indeed saying, well, if I have an observer, he can only see part of the space, and I should say part of even the microscopic theory. So there's some part that he doesn't see. And in quantum mechanics, what happens is that you then can see only part of the say quantum information, the bits, but there are things that you don't see that are entangled with the things that you do see. So you can count again the amount of entanglement. It also means that the description of the things that you do see is not given in terms of, say, a wave function like what Schrödinger wrote down. It's more like a density matrix, a thing that von Neumann thought about. And a density matrix is really an object that allows you to think about time, actually, because I mean, a density matrix, one way that we think about time in quantum mechanics is that there's a relationship with energy. So there's some way that energy kind of plays a role in describing time. It's called the Hamiltonian, because that is sort of how it tells that time evolves. And this is actually possible to define also using entanglement. It goes under the name what's called the modular Hamiltonian, but this is the way that time emerges. So we have some way that time can be defined even without assuming that it exists. And there's a beautiful mathematical theory already about it that also von Neumann already developed. I'm talking about whatever, more than 50 years ago, where really there's lots of very precise mathematical equations that are telling us that just from studying quantum mechanics that we can define time. And actually, it goes very much in the same way that I had in my paper on entropic gravity. The way it goes is that I have this part that I observe, say it's the right part of the space, the left part of the space I cannot observe. If I just forget about this left part, the right part, well, is described not in a very precise state. It's not a quantum state, but it's this density matrix. And then there's a time flow that I can generate just from this separation. And I don't need actually to assume time from the beginning. I mean, there's something that time really emerges from this idea. And I think that language of quantum entanglement and quantum the space-time, how that emerges. I mean, this is really where recent advances. I mean, people. I mean, I have to maybe mention other people in this context. I mean, people like Jeff Pennington, who played an important role, Engelhardt, Longliu. There's many people involved, young people also, at MIT, at Berkeley, at Santa Barbara, who are working on these ideas. It's a worldwide effort, and I think the language I just sort of am using here, which I'm sure that many listeners find difficult to understand, but it's something that our current discussions and even the conferences are about. I mean, we are using these ideas a lot actually about how time and space sort of had this microscopic description in terms of quantum entanglement.
When talking about entropy in Donald Rumsfeld, it was said that the known unknowns is related to entropy, but known implies an observer just when we hear the word known, like someone knows it. So there are two aspects of entropy. One is that it's observer dependent regarding a coarse graining, but then another is that it's somehow an objective partitioning. So I assume that you're thinking in terms of an objective partitioning. What is it that's determining this partition that nature uses?
Well, okay. Here I have to admit that the observer has to play an important role, because when we have a observer, he has access to a measurement apparatus or something like this, and you can do all your measurements. And that means you're going to be discovering more about what the state of the universe is. I mean, you can try to determine where all the things are located. You can do lots of measurements, but there are also things you cannot measure. And we have, and this also in space-time is connected to what we call the horizon. There's namely things you cannot observe are behind the horizon. There's some way that we have to split the space-time in the part that we can observe, which we call our observable patch, kind of what we call the observer's area, which we can see, but then its boundary is kind of then saying that there's things beyond that we cannot observe. And so this entropy that we are currently measuring is indeed about the things that we are not observing. And the nice thing about what we are discovering, which is kind of goes back to these laws of Bekenstein and Hawking and Ryutak and Yagi, is that this amount that we cannot observe is exactly measured by this area of the horizon. And I admit that in defining this very precisely, I think we need the observer by saying, well, we define what we know as the things that we can observe in principle. It does not like we have to observe it, but we have to sort of at least be able to do this by some measurement. But then there's the part that we cannot never observe, and that part we then called basically the known unknowns, because there's some way that we can calculate, or at least we have an estimate of how much is not known or not accessible to our measurements.
So the person listening, what if they're saying, just a moment, Professor, are you saying that I, as an observer, the gravitational dynamics depends on how I arbitrarily coarse grain, my choice?
No, this is not the case, because I mean there's some way that as I said, the actual thing that you are not observing or not know is more like a matter of principle. I mean, if I say you can in principle observe everything, I mean there's some way that you can measure lots of things. If you decide now to want to measure the distance to a certain star very far away, and then you can in principle do this. But even if you decide not to do it, doesn't mean that it suddenly becomes an unknown. I mean, there's some way that we have to sort of say that information that is accessible or known in a certain way is what in principle can be measured. I mean, there's some observable part of the universe that indeed corresponds to the things that are, I would say, are known. So we do give, if we talk about observers, we give them lots of power in terms of being able to observe everything that they could in principle observe, in terms of at least our mathematical equations.
Do you imagine that gravity's attractive property is just statistical, and that it's just if you were to observe close enough or for long enough, you would see fluctuations? Some moments where it reverses or vanishes potentially.
Now, I don't have a theory that predicts any of that, but I do think that in quantum mechanics there is always fluctuations, but that the fact that gravity is attractive is a very fundamental fact, that it's not something that we're going to change in any way. But I do think that as I said, that the gravitational laws can change in certain situations, and especially. And this is one of the things I already thought about when I thought about this idea of entropic gravity. When the gravity becomes very weak, I mean, if you think there are deviations and they're very small, they are more easily seen when the gravitational force that we would calculate is not strong but very weak, because then these fluctuations or these deviations might actually exceed the actual uh, strength of the gravitational force, and that's what I found so amazing when I learned about these effects we observe in galaxies. Is precisely when the gravitational force and the acceleration due to gravity becomes very small, that we are seeing these deviations. So it's related to the strength of the gravitational force when the deviations occur. And so you might say this is a fluctuation, but it's not like it's going to be suddenly repulsive. I don't think that is the actual change that is going on. But again, I don't have a full theory that explains or even predicts any of that sort.
Does entropic gravity, your version, have any bearing on the cosmological problem? The cosmological constant problem, sorry?
I think the cosmological constant problem, I think we can solve this. I mean, it's not like, I think the problem arises precisely if you start thinking about it in the way that Wilson did, by saying that the only fundamental scale is the scale at which we cut off things in the UV, in the very short distance, because then you expect this cosmological constant to be very large. I think our universe has another scale, which is a very large scale, and somehow this has to come into the microscopic description. I don't think we, in the end, will have to deal with this problem in any serious way. And I think even in ADS-CFT, which is this anti-de Sitter space, I think we basically already solved it there, because there we would have had the same problem as well, but we don't see it. And so there's some way that this problem, I think, I mean, maybe I should call it a red herring, because I think it's not something that we should worry us too much.
You said it's because the large scale may have some influence over the small scale. Now, there's this echo of that in your calculation for the Milgram acceleration. Do most physicists think that A0 equaling CH divided by 6 is a coincidence, just a numerical coincidence, like Dirac had his large number hypothesis, and most physicists that I speak to think that that's another a form of numerology. So, how do your colleagues view that Milgram acceleration?
Well, I have to say that there are really separate, how to say, sociologically separated in the sense that people either think about dark matter and then they're very much influenced by the ideas that it's a particle, or by the fact that it has to explain the CB and so on, and then there are the people that think about quantum gravity, and they don't think about particle or dark matter at all. I mean, so they have not even thought about this question. And even the community that really thinks about dark matter, I think, is split between the people that are doing observations, like astronomers, and the astronomers, they are really struck by this fact that Milgram's description works rather well, and so there's something that needs to be explained there. And I think that the particle dark matter community is not always playing this game honestly, because what they're doing is actually making models and having certain effective calculations that seem to reproduce what Milgram is saying, but I don't think they're really explaining his findings. And so, anyway, I think this is, as I said, more of a sociological thing. But certainly, the people in my field are not even aware of this whole coincidence between the value of A0 and the cosmological. I think it's not something that's generally known. And I even didn't know about it. So I had written my my theory about entropic gravity, and then I learned about this. And this is when I started realizing there might be a connection, but it's not something that was on my radar before that. And I think it's something that many people have ignored. And as I said, that's because it's simply different communities thinking about these ideas, these different concepts.
The sharp-eared listener probably heard that complexity was mentioned a few times, and then it was brushed aside because it may be too complex to talk about complexity. But what is the minimum that someone should know about complexity and its bearing on your theory?
So complexity is a way in which information can also be hidden, and we talked about that we may not access certain amount of information. And it's actually a notion that was developed in quantum computing, in the sense that if you think about computers, they do certain operations on your bits and so on. And then you can ask, how many operations do I need to do before I get a certain result? If I want to sort of extract some information from a very complicated database, then you can search for, that amount of information. And you can think about it as a very big library. If you want to find a book in a very big library, you will have to do many searches. And so the number of steps that you need to do to find something, that is basically complexity. So if you want to do a quantum computation or another computation, how many operations do I need to do to get a certain outcome from a calculation or from a search? And so this can also be applied in physics, in the sense that I talked about black holes, indeed, about how they might maybe emit particles and so on. One of the things we also worry about is that, is any information that we throw in, is it eventually lost? Can we recover it eventually? There's also a question about, maybe you can recover it, but it might require you an enormous amount of calculation. And then it becomes a very complex operation. So even though it comes out, it might be inaccessible because it takes you a very long time to compute.
Yes.
To use a quantum computer. So complexity is basically how many computational steps do I need to do, and also in our description of the way that space-time works, or even how it emerges, we are using many ideas that are actually the same as what we use in quantum computers. I mean, we think about also quantum computers are based on entanglement. They also based on qubits and all kinds of way in which information is being transferred. I mean, one of the ideas I'm currently working on is also that how do we transfer information in a quantum computer? We cannot take the qubit and bring it somewhere. We usually teleport it. I mean, there's something called quantum teleportation, which is also an operation that needs some steps to do it. And how many qubits I'm teleporting also will determine how complex it is. So there's some way that complexity, teleportation, or all the steps that we do in quantum computers somehow play a role also in describing this microscopic theory of space-time. And in particular, the interior of black holes seem to be a place where this complexity becomes very large. And that is why, indeed, maybe we don't see it, is because, well, maybe it's still accessible, but for us, it's too complex to be able to decode it. And so if you think about a black hole, it might be hiding information, not because it's not in our reach, but has been encoded in such a complex way that we have no access to it, because in order to see it, we have to do this very complex calculation. And the current discussions, and actually I already mentioned the conference that was happening in Princeton last month, I think these notions of complexity also play an important role there. I mean, there's a way maybe that quantum complexity is going to be more important to describe our universe than maybe quantum entanglement. I mean, there's this additional ingredient that's going to be needed in understanding better how we describe universes like our own.
What was the conference you just went to a month ago?
This was a conference on the Institute of Advanced Study in Princeton. That's the same institute where Einstein was during the last part of his life. But it's also a place where my brother actually is at Princeton University, so he's close by. But Maldacena is there, people like Ed Witten. But what happened in the last years is that every December they had a meeting. And maybe I should explain the title of the meeting. I mean, the person that really initiated the idea that information is the most important language of our universe is actually John Wheeler, also a professor I knew actually when I was at Princeton.
Oh,
he died two decades ago, but he was really the founding father of many ideas. I mean, he coined the phrase black hole. I mean, he thought about this term. He was the advisor of Feynman, and he had many other beautiful ideas. He also asked Bekenstein to think about what was happening to the information of a cup of whatever coffee that drops into a black hole. And this is sort of what made Bekenstein think about these questions, Hawking. But what John Wheeler did further, and that's something that he did, I think, towards the end of his life, actually, he was very much in this idea of that information was the most fundamental language of nature. And so he had a phrase for that, again, a slogan, it from bit, it was called.
Mm-hmm.
And this idea is that namely it, which is the information, is the matter, sort of the things that we know, I mean, that we can touch, but it has to arise from information, which is the bit. So it from bit is really the summary of the idea that information is more important than the things that we derive from it. I mean, the particles are derived from information. Space-time is derived from information. So it from bit. But now, with this whole quantum question, we've changed this into a slogan that's called it from qubit. We make this bit into a qubit, which is this idea that zeros and ones can be sort of in superpositions. And so the meeting that I was at actually is from a consortium that was already active for, well, I think more than 8 years. It's called It from Qubit.
Yes.
So it's really where we are discussing the question of how to derive space, time, matter, and everything from just fundamental quantum information. And so this consortium, I think, already stopped because, I mean, they were funded by the Simons Foundation from Jim Simons, but they don't have the funding anymore. But they continued, and they had now this sort of next meeting in that series, and there was lots of discussions about well, what I call baby universes, or things that are kind of like closed universes, like our own, that were obtained from ideas by using, well, this ADS-CFT or some more quantum microscopic description. And so I think, as I said, I mean, there's lots of people working on this, and there's lots of developments and ideas happening where we are using the language of quantum information, quantum entanglement, quantum complexity to study the emergence of the space-time and the gravitational laws. And anyway, so I believe this will lead to further progress in understanding also how it works in our own universe.
How do you personally choose what research programs to work on or research directions to take?
I do, of course, follow what other people are doing, and sometimes idea resonates with what I'm thinking about, and I also think that I need to learn what other people are working on, because I do think that other people have very bright ideas as well, and they may contain the tools that I need to also develop my own theory. So I do look at what ideas are around there, and the ideas that kind of seem useful or very relevant for what I'm doing. And again, we talked about the intuition, or what I developed when I was already actually as a student. There's some way that you do feel that, this is something that I think is in the right direction, and you kind of resonates with your own thoughts. I have a long-term vision of where I want to get to. The difficulty is putting all the ideas into equations and writing it down in a way that my colleagues will sort of understand it. But if I learn more about how they are thinking, and what are the new insights that they are generating, I can even make more progress myself. So working together with our colleagues, I think, and having discussions, and having also younger people entering the field, that is very important for having this whole program sort of be successful. I cannot sit by myself and simply work on my own and work out these equations. There's more ideas I need, and more input from other people, and hopefully also some young people will come around, and they will pick up these ideas, and they will take the next step. It's not like I have to do it all by myself. Actually, this is usually also not the way that physics works. It's usually one person makes one step, and the next one takes the other one, and there's a lot of collaboration and discussion going on. And I also involved actually in organizing many of these meetings, where we are meeting and discussing, also within Europe, and of course also in the US. But no, I'm happy with also the fact that there are many young people that are thinking about these questions, and very clever people that are also thinking about new ideas. And you have to indeed be a bit selective about what ideas you follow, but here a matter of taste, and also just maybe a sense of what direction you have to go into, is then necessary to select those problems.
So you keep an eye on the field, but you still follow your own nose.
That's correct. Yes, that's the way that I think, as I said, every scientist should work, is that they should have a feeling of, first of all, what they're good at, but also what they believe is the right direction.
Interesting. How do you sharpen that feeling of being on the right track? Now, obviously, no one knows if they're on the right track, but you have some intuition. And many students, I'm sure, I spoke to Susskind about this. Many students, they tend to look at their professors and say, okay, what should I be studying, or give me a problem to work on. And Susskind was lamenting that when he was younger, he would look at his generation, would look at the professors and almost sarcastically think they don't know what they're talking about. Like, we are the ones that got to come up with the new ideas. I mean, he was joking a bit.
Now, in a certain way, this is true even because I started doing my PC with my brother, and that was Robert Dijkgraaf, and I have another colleague, Karel-Jan Schoutens, and we were in the group of Gerard het Hoofd, who if I now think about, was probably in late 30s, whatever, maybe almost 40, but he already told us, het Hoofd told us. It may sound strange, he said, but I'm already an old guy, you should do it. And we were like 23, 24. And this is where we already decided that we should sort of go ahead and follow our own nose. We didn't. And I have to admit that I don't think it's necessary to look at your professor and say, I want to follow what he's saying. No, you should have your own feeling of what is the right direction. I think this is what makes, I think every great a physicist, a theoretical physicist, should have already this this talent. And I think following what other people are doing is not going to bring the next idea. I mean, you have to follow your own ideas. I mean, you have to go beyond what other people are doing, because if you just follow, then yeah, you're not leading. I mean, there's some way that you have to be the first one to have an idea and not the second one. I mean,
what's a piece of advice from David Gross and Ed Witten that stuck with you?
I think with Ed, he always said, indeed, also that you want to work on the things that you're also good at. I mean, it's something that I mean, you cannot solve all problems. I mean, you have to work on the problems that you feel that you're good at. Anyway, that's something that I learned from him. But also, I mean, I of course also look at the way they do work. I mean, they are very precise in terms of how they do. I mean, Ed is more mathematical in his way of working. David Gross asked the big questions. I mean, this what I learned from David Gross is that you really want to understand how nature works. I mean, this is really what makes him excited, and also as an example, I mean, he radiates a certain joy in thinking about big questions, and I always think this is also how I feel, is that I'm very lucky to be thinking about questions that I'm interested in, and having colleagues like him is inspiring. I mean, I think the mentoring is not just giving advice; it's really just also leading by example. I think that's maybe how I see that.
Now, to wrap, I want to go all the way back to the beginning with the turtles. So, when speaking about what does a good question look like, it sounded to me like you were saying it's to discover what the next turtle is. So, in other words, make some progress. Don't think you're going to make the ultimate progress. Make some progress.
Yes.
What I want to know is, in your mind with the infinite turtles, do you imagine that that's actually how nature is? Or do you imagine that there is a bottom turtle?
No, I think I'm already going much further than most of my colleagues are. They're very happy to sort of work within the current framework, and I think there's a next theory to be discovered, a next turtle, and that makes me happy in the sense that I feel there's some big thing to be done. If I start thinking about the one underneath it, I'm also lost. I mean, I have no idea. And so I want to be thinking about the next one. And I feel that we are on the verge of making a totally new theory of the gravitational force and of space-time. I mean, if you think about this in the perspective of how science progresses, we went from Newton, who had a very beautiful theory where we felt that maybe that's the final thing. That's certainly what they thought in the 19th century. Then Einstein came along with quantum mechanics, and suddenly people were very happy, but also confused. And I think we're now at a level where we are replacing those theories, maybe not quantum mechanics, but certainly general relativity, by a new theory where we go beyond what we thought was space-time and so on. I don't think it's a final theory, but at least it's one step further. And this is the theory I want to be contributing to. So I'm not thinking about the next turtle or the one underneath. But I think the fact that we have to make a jump to the next one is important. But what helps me is that I'm not thinking about it as the final theory. If I would
Mhm.
think about it as the final theory, I would start thinking about it differently.
I want you to take off your physics hat and put on a metaphysics hat. What I want to know is I know that you believe that all we have access to, or perhaps all we should focus on, is the next hurdle. But what I was asking was something more along the lines of you make some propositions, call it proposition X. And then I say, well, why do you believe that? You say reason A. And then I say, but why do you believe that? You say reason B. And then I say, but why do you believe that? You say reason C. And then I ask you again and you say reason A. Well, we would say that's circular, and we wouldn't like that. Okay, but that's one route people can take. Another one is to just say, well, reason C, and I ask you why reason C, and you say reason C is axiomatic. I can't go further. And another one is to then go, well, reason C because of reason D, because of reason E, dot, dot, dot. And you just keep going ad infinitum, pretend there's infinite letters of the alphabet. So those are three routes one could take for justifying something: axiomatic, circular, or infinite regress. What I wanted to know is, do you believe that the universe actually has this infinite regress? Or do you believe, well, Curt, this is a foolish question. You're just asking me something out of my wheelhouse. I'm a physicist. This is too philosophical for me. Or do you believe that there is a foundational layer? Or do you believe it's circular?
Um, so you think as a logical um, way in which the universe works. Well, there may be an end. I mean, it's true that the the turtles all the way down has more to do with what we are capable of as humans. I think the universe might have a finite way in which it's describing itself, but one of the assumptions I always think that I like to believe in is the following: that suppose there is a way of describing what's going on in the universe, and you could put it on a computer, and it would calculate what would be going on. We would be able to make predictions. Any prediction. I think any system of that sort will fail. I think that the best computer to run the universe on, is the universe itself. So there's no more efficient way of summarizing what is going on in the universe than the universe itself. So any smaller thing that would try to do it will have to make an approximation. You have to throw away something. The universe itself is the most efficient way of making the universe work. I mean, it's also for me a very reassuring idea. I mean, what if there is a glitch in the code of the universe? In the sense that there's some bug there that may make the world end tomorrow.
Mm-hmm.
The fact that that doesn't happen, I go to sleep and I wake up. I know I kind of wake up tomorrow. I mean, my own health is the only thing that I worry about, but the universe will not stop. So it's not like the universe may have something wrong about it, or maybe that its equations kind of are not perfect. No, I think the universe is a perfect thing. But I feel this is also what is emergence. I mean, if I think about even consciousness or life, which are very important and difficult questions, I think the way we should understand them is also in terms of emergence. Everything like that is emergence. And in a certain way, even this grand design idea, maybe there's some intelligent design, all those things. But I feel that if a universe works in a very, I think emergence actually is the way make things as efficient as they are now. I mean, I have this colleague, Robert Dijkgraaf, quite a famous guy, but he makes very nice talks also where he says one of the things that physicists were looking for a very long time is beauty. something that makes a very beautiful thing. But there's also something about nature that's sort of more like garbage, where if you look at the next layer, it looks like garbage. And in a certain way, beauty can come from garbage, but even garbage can come from beauty. There's, if you write down the equations for the standard model, they're very beautiful. But if you make a very complicated thing, it can become very complicated. But then there's again something very beautiful. So this is a little bit related to these layers. If you read the little books by Feynman, he kind of says the very same thing, that somehow in the progress of nature we have seen these steps where something looks complicated and suddenly it becomes beautiful again. The 50s was like this, where people discovered many hadrons, mesons, and it looked like a mess. And then suddenly there was the quark theory. It was very simple. It was very beautiful again. I think that in the end, it's chaotic. I think our fundamental equations probably are chaotic, and that the beauty or the structure that we see are just arising from that chaotic description. Now, by the way, now one final comment. Maybe we didn't talk about this at all, because if you really ask me, I have my big goal, actually, and actually my big even frustration with our current laws of physics is that I'm not happy with the way we are describing the beginning of our universe. I do think that the things like inflation or even Big Bang and all that stuff is only approximation of what really happens. And I think this idea of chaos or even quantum chaos is something that we talked about complexity, but we didn't talk about quantum chaos, which I should have mentioned. Is also one of those very important concepts that if you ask me where does the world come from, probably my answer would be quantum chaos, really a chaotic microscopic theory.
So you're not saying that inflation or the Big Bang didn't happen. You're just saying that that's not the full story. That's an approximate story.
That is an approximate story, but I mean, in the sense that what I mean, if it doesn't happen, it really means that it's not the full story, and it's also just an approximation. But it's also telling us that we have been ignoring a lot in our description of the early universe. And this is where my approach is different. And actually, this also makes the idea of emergence of a much more of a important concept in my mind, because emergence always means that there's something underneath that you may not sort of fully describe or understand, but you can at least understand the equations that follow from it. And again, the most beautiful example I know about is how Boltzmann got to the laws of thermodynamics. He had no ideas what the atoms were or the molecules were at a microscopic level. He didn't know about the periodic table and all that stuff. Nevertheless, he could derive the laws of thermodynamics simply by assuming there were molecules and atoms. So in a certain way, I think we're doing the same thing. We're assuming there's a microscopic language in terms of quantum information, and we have some examples, but I don't think we will discover the microscopic description of our universe. But we do understand the general principles by which our laws are derived, are emergent. I find that's a beautiful thing to work on, and that's what makes me happy. And I will be doing that for the next whatever decades, I think. So I hope.
Well, sir, I found this conversation beautiful and it made me happy. So thank you.
Thank you, Curt. I enjoy this too. Thank you very much.
Hi there, Curt here. If you'd like more content from Theories of Everything and the very best listening experience, then be sure to check out my Substack at curtjaimungal.org. Some of the top perks are that every week you get brand new episodes ahead of time. You also get bonus written content exclusively for our members. That's CurtJaimungal.org. You can also just search my name and the word Substack on Google. Since I started that Substack, it somehow already became number 2 in the science category. Now, Substack, for those who are unfamiliar, is like a newsletter, one that's beautifully formatted, there's zero spam, This is the best place to follow the content of this channel that isn't anywhere else. It's not on YouTube. It's not on Patreon. It's exclusive to the Substack. It's free. There are ways for you to support me on Substack if you want, and you'll get special bonuses if you do. Several people ask me, like, hey, Curt, you've spoken to so many people in the fields of theoretical physics, of philosophy, of consciousness. What are your thoughts, man? Well, while I remain impartial in interviews, this Substack is a way to peer into my present deliberations on these topics. And it's the perfect way to support me directly. CurtJaimungal.org or search Curt Jaimungal Substack on Google. Oh, and I've received several messages, emails, and comments from professors and researchers saying that they recommend Theories of Everything to their students. That's fantastic. If you're a professor or a lecturer or what have you, and there's a particular standout episode that students can benefit from, or your friends, please do share. And of course, a huge thank you to our advertising sponsor, The Economist. Visit economist.com/toe, TOE, to get a massive discount on their annual subscription. I subscribe to The Economist, and you'll love it as well. Toe is actually the only podcast that they currently partner with, so it's a huge honor for me, and for you, you're getting an exclusive discount. That's economist.com/toe, TOE. And finally, you should know this podcast is on iTunes, it's on Spotify, it's on all the audio platforms. All you have to do is type in Theories of Everything and you'll find it. I know my last name is complicated, so maybe you don't want to type in Jaimungal, but you can type in Theories of Everything and you'll find it. Personally, I gain from rewatching lectures and podcasts. I also read in the comment that Toe listeners also gain from replaying. So how about instead you re-listen on one of those platforms like iTunes, Spotify, Google Podcasts, whatever podcast catcher you use, I'm there with you. Thank you for listening.